Hello, this is a lecture on section 2.2 of linear algebra by David Lay, and this is Karen Edwards talking to you and making annotations on the transparencies. For this particular video capture, I'm just trying to give my class enough material to do the problems that I want them to do on the homework and enough to be able to do similar problems on the midterm next week. I'm not going to cover the whole section. I'm just going to cover the basic computations of how to compute the inverse of a matrix and the single most important upfront example for using it, which is to find the solutions to the pre-image of a point under a map when possible. So I'm gonna go through pages 1, 2, 3, and 9 and just focus on that material. So at the beginning, the inverse of a matrix is similar to the inverse of a real number, which is the number that you multiply it by to get back to the identity. So with regular numbers, as shown here, fancy silly dotted thing, sorry. I don't know what system I'm in, just cut that. Erase, okay. Sorry, I thought it was in a different mode. So, real numbers. With a real number like 7, you multiply it by the inverse of 7, and it gets you back to 1, which is the multiplicative identity. So similarly with matrices, suppose you start with a matrix A. If there is a matrix C that you can multiply by it to get back to the identity, and you have to be able to multiply A by C on either side and get the identity both times, then C is called the inverse of A. It's the same idea. What do you multiply by to get back to the identity? And as with real numbers, if there is an inverse, then it's unique. There's only one possible inverse. Okay, so I'm going to skip the proof stuff right now and focus on, let's see, page 2. Okay, so here is the computation. There's a shortcut formula for 2 by 2 matrices. So if you have a matrix A, B, C, D, then if this little expression AD minus BC is not 0, then you can find the inverse. And the inverse turns out to be 1 over that expression, and then you swap the A and D, swap places, and then the B and C get their negatives. So that's a cute little formula for the inverse. So let's try that out with an example. Suppose I have A equal, and I'll just use generic numbers, 1, 2, 3, 4. Okay, then to compute A inverse, I'm going to leave a little space in front here. Well, I'll go ahead and I'll do that part first. So it's 1 over 1 times 4 minus 2 times 3. You might notice that that's the main diagonal minus the other diagonal is the easy way to remember that. So 1 times 4 minus 2 times 3. And then in the matrix itself, we swap the items on the main diagonal, so they become 4 and 1. And we take the opposites of the other two numbers, -2 and -3. So in this example, sort of fitting this around, there wasn't any other space on here to do this. So 1 times 4 is 4, minus 2 times 3 is 6, so 4 minus 6 is -2. So there's a -1/2 in front, and then our matrix is 4, -2, -3, 1. Let's test this to see what happens. So if you multiply A times A inverse, we're multiplying 1, 2, 3, 4. The scalar can get multiplied in any order, so I'm going to write the matrix of A inverse first. 4, -2, -3, 1 times -1/2. And then, computing that, to multiply these two matrices, we're going to do the row-column method. So, ooh, I think I can do this a cute way. Hang on. Okay, so if I do 1, 2 times 4, 3, if I do that dot product, then it's 4 minus 6, which is -2. And I'm going to erase those. And that's a -2 that goes there. Okay, next I'm going to do the 1, 2 times the -2, 1. That dot product is -2 plus 2, so that gives me a 0 in that position. Next, I'm going to do the 3, 4 dotted with a 4, -3. That's going to be 12 minus 12. That gives me a 0 down there. And lastly, the 3, 4 dotted with the -2, 1. That's a -6 plus 4. This is starting to look a little familiar. So that's a -2. Okay, back to our green. Oops, wrong green. Sorry, not a big deal. Okay. And then that is times -1/2, so that gives us the matrix -1, 0. I'm sorry. Well, I'm starting to use this backup button more. I like it. Okay, so that gives us the matrix 1, 0, 0, 1, which is the identity. So this A inverse did exactly what it was supposed to do. We multiplied it by A, and we got the identity. I assure you and encourage you to check on your own that in the other order, A inverse times A would also give the identity. Okay, so that's how you find the inverses of 2 by 2 matrices. Remember that it relies on this fact that AD minus BC is not 0. If you had a situation where it was 0, you'd figure out pretty quick that the inverse didn't work because you'd be trying to divide by 0, and you would say to yourself, this looks suspicious. So it doesn't work exactly when you try it and it doesn't work. Okay. Next, so that was 2 by 2 matrix inverses. Next, I'm going to show you guys the nicest way to use these inverses. This works in general, not just for 2 by 2. So this is back to linear transformations and trying to find vectors that map to a given vector B. And we've done this several times now. So we have a domain and a codomain. Remember, we've got sort of T from domain to codomain. And in the codomain, we have a vector B, and we're trying to figure out what vector maps to it. And the way to figure that out is to solve the system of equations, AX equals B. So we know A, that we know the matrix A, we know the vector B, we don't know the vector X. That's what we're trying to find. So instead of solving the system of equations, which is what we're used to doing, which works perfectly well, there's a cute option. What happens if we multiply A by A inverse? Let me do that with another color. What happens if we multiply in front by A inverse on both sides? This is a legitimate operation, so you can always take both sides of an equation and multiply it by the same matrix, as long as you always multiply it on the same side. So if we multiply on the left, then we always have to multiply on the left. If that's defined at all, which if the matrices are the wrong sizes, they won't be. But in this case, if A is invertible, then you can certainly multiply it by its inverse, and you do that on both sides of the equation. What happens? Well, A inverse times A becomes the identity. And that's equal to A inverse B. And the identity times X, well, what's the point of the identity? If you multiply it by a vector, you leave it alone. So you get just x. So that means x equals A inverse B. This might seem mysterious, and I'm sorry there's so much written on one page here. These slides are still more compressed than I would like. So this other stuff goes over there. And now to explain why this makes so much sense, it's the same thing. Let's see, let me erase this here. So similar to what if we're just dealing with regular old numbers and I say solve 3x equals 7. So the number 3 times some mysterious number x, and you get the result 7, and you want to know what x is. How do you find x? You divide both sides by 3. So that's the same thing as really using the red here to match. If I multiply both sides by 1/3 times 3x equals 1/3 times 7. That's really the same thing as dividing both sides by 3. But specifically, what am I doing? I'm multiplying by the inverse of 3. Why? Because then the 1/3 and the 3 cancel out, and I'm left with x equals 1/3 times 7. That's exactly the same thing that we are doing with the matrices. We have matrix A times x equals b. To figure out what x is, we multiply by the inverse of A to get rid of the A and have x by itself, which means on the other side we have A inverse times b. So that's our nifty new little way to solve for x in these situations. Okay, remember you can also solve the system the same way we've been doing it for a while. This is just a new method. Okay, the next little bit here I'll comment on, which is when you do this, okay, remember when we had vectors B and matrices A, and when we solved this system, sometimes there were lots of vectors that were the answer. Sometimes there were infinitely many vectors that all got sent to B. That can't happen here. This has to be the case where it's only a unique vector x that gets sent to B. And that's because A is invertible. Because if there was some other vector w, so suppose w is also a solution to ax equals b, so then aw equals b. So in other words, suppose you have ax equals b and aw equals b. Both x and w get sent to b. Well, if we do the same process, multiplying by A inverse on both sides, then these cancel out. We get W equals A inverse B. But also, X equaled A inverse B, which means they're really the same thing because they're both equal to A inverse B. So you can't really have two different things getting sent to B because whatever it is has to be A inverse B, and that's only a single vector. So there's only a unique solution in this case. Prove the following result. If A is invertible, this all relies on it being invertible. In those cases, when you solve ax equals b, then you can do it using this cute trick, and the solution you get is unique. There's the cute trick. Okay, so that's why we're going to use it for starters. The next page is an example. So this is the basic kind of question that I might ask you on the homework in the midterm for this week. So here's a system of equations. You don't have to think of it as a map. In general, it's really just any time you're solving a system of equations. Here's a system of equations you're solving. It's got the corresponding matrix A, which is -7, 3, 5, -2. Here's the matrix form of it. And our cute way of solving it is going to be to multiply before each, on the left-hand side of each side, we're going to multiply by A inverse. We just have to compute what it is. So A inverse equals 1 over the main diagonal minus the other diagonal. So that's -7 times -2 gives me the 14, minus 3 times 5 gives me the 15. And then for the matrix itself, we swap the entries of the main diagonal. We swap the -2 and the -7. We take the opposites of the other two entries, so the 3 and the 5 turn into -3 and -5. And that's the inverse. We just simplify because 1 over 14 minus 15 equals -1, so the -1 gets multiplied by everything, and you get the nice matrix 2, 3, 5, 7. So what we're really going to multiply here is 2, 3, 5, 7, and sticking it in on the other side, we are multiplying by 2, 3, 5, 7. So these guys are going to cancel out. You can test that. You should test that. See if you get the identity by multiplying. And that means that the solution x equals A inverse times b. So that's 2, 3, 5, 7 times b, which is 2, 1. And now we just multiply that matrix times that vector. Oops, so I'm inserting a clip here. I made a careless error the first time and had all of this work here, which is incorrect. So I'm going to fix it now for those of you who watched the original version. It turns, I don't know why I did this, but I put a minus there instead of a plus. So computing the matrix 2, 3, 5, 7 times the column vector 2, 1. We start with the row 2, 3 times the column 2, 1. That should be 2 times 2 plus 3 times 1, which is not 1. That's 7. And then the row 5, 7 times the column 2, 1 is not 3. That's 17. Thank you so much to the student who emailed me to point this out. So 717 should have been the correct answer. So just to fix the rest of this, that means the unique solution is 717. Again, it's unique because we found it by multiplying by the inverse. That will always give you a unique solution. And now if you want to test this, you can put the vector 717 in here and see if the matrix, and I'm missing a -2 down there. Wasn't that the original matrix? Sorry, -7, 3, 5, -2. Yep. Okay, so that original matrix A times the vector we found, x, should give us the result we want, b. And now let's do this carefully. -7 times 7, -49. 3 times 17 is 51. So 51 minus 49 is 2. And then the bottom row, 5 times -2 times 7, 17. So that'll be 35 minus 34, which is 1. So 717 is the correct answer. So if you could check that a different way by substituting x1 equals 7, x2 equals 17 back into the original system that was up here at the top. And it should also make those work. Okay, so now I'm going to jump forward to page 9, which is skipping a little bit of stuff. Skipping a lot of interesting theoretical stuff, and it's also explaining why the algorithm I'm about to show you works. So after showing you this algorithm, if you're asking yourself, oh my gosh, that is so cool, why does that work? Then you can go back and read some of the previous pages. If I have a chance, I'll get to them later in class, but wanted to start by showing you the algorithm. So this is how to find the inverse for any square matrix. I didn't emphasize this before, but in order to have an inverse at all, it must be square. Otherwise, it's hopeless. It just turns out that if you have a non-square matrix, there's no way to be able to multiply it on both sides by some other matrix and get the identity. It doesn't end up working. And we will hopefully get to the theoretical reasons for that. So if you have a square matrix, it might be invertible, it might not. And the way to find out, here's just this little bit of theory. So it's invertible if you can row reduce it down to the identity. If you can row reduce it down to the identity, then it turns out if you start at the identity, and row reduce it using those same row operations, you get the inverse, which is super cool. That's where your curiosity might be piqued and you might go look at the previous 3 pages. But here's the basic algorithm. So you create a matrix with A on one side and the identity on the other side, and you use row operations that reduce A to I, and those same exact row operations will reduce I to the inverse of A. Magic. Okay, so here's an example. Sorry, I'll put the little augmenting thing there. So suppose we're trying to find the inverse of this matrix, 2, 0, 0, negative 3, 0, 1, 0, 1, 0. Okay, we put that in the left half. There's our little reminder, A and I. So we put A in the left half, and we put I, the identity matrix, in the right half. Now we do a bunch of row operations, and all we're looking at is the left half when we decide what row operations to do. So we look at the 2, 0, 0, negative 3, 0, 1, 0, 1, 0, and we decide what row operations we're going to do to turn that into the identity matrix. But every time we do a row operation, we're still going to apply it to the entire row. We're going to apply it to that identity matrix on the right. So once we've strategically turned A into the identity matrix, it turns out that the identity matrix on the right-hand side turns into this guy. And that's going to be A inverse. You can test it. So i.e., if you multiplied 2, 0, 0, negative 3, 0, 1, 0, 1, 0, and you multiply it by 1 half 0, 0, 0, 0, 1, oops, I wrote that down wrong, 3 halves 1, 0, then you should get the identity. Again, you can test that yourself. But this one's fairly easy to test because there's so many zeros involved, so you can actually just eyeball most of that and see that it's totally believable. Yes, I get the identity. Okay, so those are the basic things to cover here, which is the inverse of 2 by 2 matrices, the inverse in general of n by n matrices, only square matrices should apply for this process, and then the basic application of this, which is it's another way to solve the matrix equation AX equals B. That's all for now. Good luck.